One of the several people have asked about clarification regarding this common emitter amplifier with emitter degeneration here. Okay, so let me quickly explain. So the issue was that we have an amplifier like this, simple amplifier, and what we have seen with this particular amplifier is that the transistor is nonlinear, and therefore the distortion, the output is distorted, and distortion measured in total harmonic distortion, THD, increases with the magnitude of the input voltage here. The voltage that I apply between the base and emitter junction here. And as I increase VBE, the harmonic distortion in the output also increases. And as a rough rule of thumb, if the base emitter voltage is 5 millivolt, I would get roughly 5% harmonic distortion. If the base emitter voltage is 10 millivolt, I'll get 10% as a rough rule of thumb. Okay. So the issue was, and as an example, we have shown over here that if I take this particular design and I apply 10 millivolt sine omega t, 10 millivolt is the magnitude, and we look at the sinusoid, we see that the positive peak is different from the negative peak, an indication of distortion. The fact that positive peak here is only 0.75 and the negative peak is -1 indicates that there is significant harmonic distortion. And if we calculate, or if we through the simulator, we find is 9.6%. So 10 millivolt of input, this 10 millivolt that you apply here, almost all of it goes across base emitter junction and gives rise to 10% harmonic distortion. Now the issue is, suppose I have a signal which is 20 millivolt. I have a 20 millivolt signal here, and I want to amplify that signal. If I apply it directly 20 millivolts, I would get harmonic distortion of close to 20%. For example, if I take the same circuit, I apply 20 millivolts, I'll get 18.6 or close to 20% harmonic distortion. Now, I don't want that. I want to amplify a 20 millivolt signal with 10% harmonic distortion. That's the problem. I don't want higher harmonic distortion, but I would like to amplify a 20 millivolt signal here. So as I said, a very simple solution is, not a good solution is, you take 20 millivolt, use a voltage divider, make it 10 millivolt, and apply 10 millivolt here, and you'll get 10% harmonic distortion. Okay? But that's not a good strategy, because you're building an amplifier and you're taking a signal, you're attenuating it first, and then you're amplifying. Doesn't make sense. Okay? So another way of doing this is what you do is you add a resistor in the emitter. You add a resistor in the emitter which is present under small signal condition. Okay? We have seen that we've added a resistor for biasing purpose. We are not talking about that particular resistor. Adding a separate resistor for small signal purpose. And, when we do the analysis, what we find is that there are many benefits of this particular resistor. One of them is that it allows you to increase the input resistance. Input resistance is R pi multiplied by 1 plus GMRE. So input resistance increases of this amplifier, but at a cost, which is that the gain drops here. Gain drops from GMRC. If I didn't have RE, the gain would have been GMRC, and device drops by 1 plus GMRE. So that's something that we have seen. Let's come back to the issue that we are talking about. I have a 20 millivolt signal, and I want to amplify it. And we said that to manage distortion, we would like to keep this voltage as 10 millivolt. So now you can see here there's a natural voltage divider. This signal that I apply here, part of it will drop here and another part will drop here. So there's a natural inbuilt voltage divider in the circuit here. And one can show that the base emitter voltage, VBE, is equal to Vs, whatever you apply here, divided by 1 plus GMRE. So, my task was earlier that I wanted to amplify 20 millivolt signal. 20 millivolt signal, but with 10% distortion. So what we were looking for is, even though you apply 20 millivolts, what we were looking for is, we should get across the base emitter junction 10 millivolt. 10 millivolt here and 10 millivolt here, and that I can adjust by making GMRE product equal to 1. If GMRE product is 1, then VBE is Vs by 2. I'll get 10 millivolt here and 10 millivolt here. So we can do that. There's a voltage divider. And now this is where something new comes in. What the traditional picture would be is that when you apply 20 millivolt here and you get 10 millivolt across here and 10 millivolt across here, the harmonic distortion which would be present would be because of this 10 millivolt, and therefore it would be 10%. That's the conventional picture. Because we were seeing here that distortion is proportional to the voltage across the base emitter voltage here. So I've applied 20 millivolt, 10 millivolt appears here, so I'm expecting 10% harmonic distortion. What do I get? Well, that's what I had said here, Cedra and Smith. If you note that if they will say for the same nonlinear distortion, the input signal can be increased by a factor. So that's what they're implying, that with 10 millivolt, you should get 10% harmonic distortion. Anyway, what do I get? Well, example 20 millivolt, 10 millivolt is appearing here, 10 millivolt is appearing here. What I get is not 10%, I get lower. So I get an improvement in distortion. I get lower distortion. Now the issue that was arising in some people's mind is, why am I getting lower distortion? So 20 millivolt I'm applying here and 10 millivolt is appearing here. Why am I not getting 10% distortion? Why am I getting roughly half the distortion that I'm expecting here? And the reason that I had given earlier was that what this negative feedback is doing is that the effect of negative feedback is, so what is happening is a signal as it goes through gets distorted. What negative feedback is doing is the voltage that appears here, yes, I'm saying is 10 millivolt approximately, but the 10 millivolt which appears here itself is distorted. Is distorted, but is distorted in an opposite manner. So that when this distorted sinusoid goes through this transistor, the transistor further distorts it and sort of compensates. There's a compensatory effect. Okay, and that's why you end up with smaller distortion here. So I think this is the part that people are having difficulty in understanding. How do I get maybe a sort of a distorted sinusoid here? I'm applying a pure sinusoid, and why is the distortion here opposite to what the transistor's distortion would be? How is this happening? Okay, so let's look at it slightly from a different angle. We said this is a picture that you are all familiar with. I have an amplifier. This could be any block, and so a picture of negative feedback. You know that y by x is a by 1 plus eta a. Fine. Let's and so one of the effects of negative feedback, well-known effects of negative feedback, is that negative feedback helps in reducing nonlinearity. We all, if you're seeing distortion, you're seeing that distortion is occurring because of nonlinearity. If I didn't have nonlinearity, there would have been no distortion. So if you reduce nonlinearity, you reduce distortion. Okay, so let me show you an example here. Let's look at this case here. So we have an amplifier. Okay, just as a hypothetical case, we have an amplifier A here. Okay, right now I'm showing you the characteristics of this amplifier A only. Look at the characteristics. This is V out and this is V in. Do you see a nonlinear amplifier? What will this amplifier do to the positive voltage? It has a gain of, note 10 here and 0.1, it has a gain of 100. In the negative direction, it has a gain of 200. So it's a nonlinear amplifier. A is nonlinear. If I feed in a pure sinusoid, what will be the output of that? I feed in here a pure sinusoid. The output would be, the positive peak would be, let's say 10, and the negative peak would be minus 20. Highly distorted output. Okay. So this is my open loop amplifier. Now let me put a negative feedback and look at V out versus V in. Looking at the overall V out versus V in. Same amplifier, now with negative feedback, V out versus V in. With the eta of 0.09. See what happens? V out versus V in. After applying a negative feedback. Look at the linearity here. 1 here and minus 1 here. Very linear. So highly linear. How has this happened? So let's put both of them together. How has my amplifier, overall amplifier with negative feedback, how has it become more linear? Highly nonlinear here, A, but with a simple feedback is highly linear. So what has happened? Look at when you are feeding back the signal, if the gain here is lower, the signal which is fed back times neta is also lower. Right? And when the gain is high, the signal which is fed back, the negative signal which is fed back, is also higher. So there's a compensatory effect. In the negative direction, for example, if I have a gain of 200, but then the gain of 200 is attenuated by a larger factor, 1 plus eta A. 1 plus eta A is also larger. While in the positive direction, if my gain is only 100, it's attenuated by a smaller factor here. So there's a balancing act that is occurring here. And the overall signal becomes, overall amplifier becomes a linear amplifier. But now if you think about it, the amplifier, this A is still nonlinear, right? So if I feed in a pure sinusoid here, I will get a pure sinusoid here, correct? Because it's linear. Let's say it's perfectly linear. So if I feed in a pure sinusoid here, the output would be a pure sinusoid. But the amplifier A is still nonlinear. I've not touched the amplifier. So what will happen at the input of the amplifier then? Can it be a pure sinusoid? What will it be? The amplifier will still distort, right? The amplifier A will still distort. But then how is the distortion absent? How am I getting a pure sinusoid? Because the input to the amplifier A is a distorted sinusoid. And the distortion is opposite to what my amplifier A will do. And that's how the two things are cancelling. So if you go inside and find out how, okay, negative feedback is linearizing it, but what is really happening in terms of signals, this is what the conclusion you come to. That if this is a pure sinusoid, then this has to be a distorted sinusoid. The signal here is distorted. And the distortion is opposite to what A will do. So which means that if A's gain is less in positive direction, the sinusoid here will have a much larger positive amplitude. While if the gain is more here in the negative direction, the sinusoid here will have a much lesser negative amplitude. So that's the nature of distortion. Now when it goes through A, those two distortions cancel each other and I'll get a very nice sinusoid. So similar effect is happening in a bipolar transistor also. Same phenomenon is occurring. So when you put a negative feedback, one of the benefits that you get here is the linearization. Your characteristics, V out versus V in, they get linearized. Okay? And they get linearized and therefore the distortion reduces here. And the mechanism of distortion, detailed mechanism of distortion is that the input to the amplifier A itself becomes distorted. Okay? So this is what is happening inside our amplifier. Okay? So coming back, putting a negative feedback that you see here, yes, it attenuates. I get 10 millivolt here and 10 millivolt here. Fine, that's a simple voltage divider. But in addition to that, 10 millivolt, the distortion is not proportional to 10 millivolt appearing here. The distortion is not 10%. The distortion is 5%. Because negative feedback is helping to linearize the amplifier and you get a lesser distortion here. So two things are happening here. The signal is getting attenuated and a transistor, the overall amplifier is becoming more linear and therefore the distortion is reducing. Okay, further clarifications? If you want, what I did was I took this, if you want to play around with it, here is our amplifier, a simple amplifier. This is a nonlinear amplifier. In microcap, what you can do is this particular element that you see here is called a voltage control voltage source. But what you can do is if I double click here, I can give the characteristics of this amplifier in the form of a table, a large table here. See here? You can give a set of pair, for every input you can give what the output is, right? So any kind of an amplifier is what? Input voltage versus output voltage characteristics. So the first, it shows for minus 9.9, the output is so much, for minus 9.8 here. So you can give the graphical characteristics in the form of a table. So any kind of an amplifier, you can create whatever nonlinearity and all that you can create, enter it in the form of a table. So this is a nonlinear amplifier and this is our feedback. If I don't want any feedback, let's say I put very, very small value here, note that the sinusoid will be, if I do transient analysis, look at the sinusoid 2.5 here and look at 5 here. Highly distorted sinusoid, output sinusoid here. right? Highly distorted here because there's hardly any feedback. There's almost zero. Now suppose I put here 1K. Now look at the sinusoid, much better sinusoid at the output here. Okay, so sinusoid is becoming a much better with lesser distortion. Now, how has it become smaller? Well, you can go ahead and probe this particular point here. The voltage that is appearing between at the input. You'll see it's a distorted sinusoid. Okay, so you can do all of that. I don't want to go into the details. I'll pass on this particular file to you. You can play around and convince yourself that how distortion is getting reduced. Okay.